mathematicians. We see many interesting Nbhm PhD problem asked in the previous year exam. I want to cover 100 problems. Let's see how far I can go. And mostly we do algebra and analysis problem. Okay. Okay, let's see what is the first problem. So we'll go 2019, 18, 17 and so on. Find the number of irreducible monic polynomials of degree 2 in the field fp, where p is the prime number, p is a prime number. Okay, so this is a very simple problem, but this problem, when it's asked in interview, you should know how you got to this formula also. Let's see what is the formula to calculate the number of monic irreducible polynomials. Let mq comma n be the number of irreducible monic polynomials of degree n over a finite field with q elements. Okay, if it is a finite field, it will have q equal to p power n elements, and that q, p power n, for that q comes here, and n is the degree of the polynomial. Okay, now you have a nice formula for this number m q comma n. This is 1 by n summation d divides n Mobius function of n by d, then q power d. Okay, so in our problem, q equal to p power 1. So basically q equal to p. So let's see what is Mobius function. So Mobius function is a function from natural number to, you can say, real numbers. When n equal to 1, the value is 1, mu of 1 equal to 1. And if it is a square free number, that means that product of distinct primes, if there are k distinct prime factors for n and no prime factor occurs twice. Okay, so basically it is just simply product of k distinct prime numbers, then mu of n will be minus 1 whole power k, 0 otherwise. Okay, so you have to just substitute this number, and for example, in this problem we want to calculate m of p comma 2, degree 2 monic irreducible polynomials over the field fp. So if you substitute, you get the value 1 by 2 times p square minus p. Okay, okay, let's continue. Let p be a prime number. What is the order of a P-Sylow subgroup of G? Okay, note that if G has order of G equal to n, then if p is a prime divisor of n, if p power alpha divides n, and if p power alpha plus 1 doesn't divide n, then G has a subgroup of order p power alpha. So this subgroup of order p power alpha is called the Sylow subgroup. So let's see how to approach this problem. The cardinality of g ln of fp. So that this is a well known formula, p power n minus 1, p power n minus p, etc, etc. Now note that in each of this term you can take some power of p outside. Okay, so here you can take p outside, here you can take p square, here you can take p power n minus 1, and there will be some remaining terms. Here you cannot take out p anymore. This means that this remaining product p won't divide. So now product of this term will give me p power n into n minus 1 by 2 and some remaining terms which is not divisible by p. Therefore, this number, it divides order of the GLN fp, and its plus 1 will not divide order of g. Okay, because this remaining factor is not divisible by, so you cannot take out any more p outside. Therefore, this is the largest power of p, that is which divides order of g. Therefore, order of the P-Sylow subgroup is p into n, p power n into n minus 1 by 2. Okay, so let's see the next problem. Give an example of a Phi-Sylow subgroup of GL3 F5. Let's see. So we want Phi-Sylow subgroup of GL3 F5. So by our previous formula, the order of the Phi-Sylow subgroup is this n is the size of the matrix. So n by n matrix. Here it is 3 by 3 matrix. So it is so this is p power, p is 5 power 3 into 2 by 2. So that is basically 5 cube. Okay, so now we need a subgroup of order 5 cube. Okay, so now it is easy to construct. This is called Heisenberg subgroup. So this group has order 5 cube. Okay, this is 3 variables are there, each varies over f5. So 5 into 5 into 5, you get a 5 cube number of elements in this group. Okay, this is a Sylow subgroup. Now note that this is a non-abelian group. So any group of prime square order is abelian, but any group of prime cube order need not be abelian. This is an example of a non-abelian group of order p cube. Okay, let's continue. So like some problem in some NBHM, the beauty of NBHM question paper is different options require different approach. Okay, so if different option requires a completely different approach, I call them distinct problems. Okay, so I call 4, 5, 6. That's why. So let G be a finite group, then there exists n belongs to n such that G is isomorphic to a subgroup of GL and R. Okay, so let's see how to do it. Take a finite group. So basically we need to recollect the proof of Cayley's theorem. Cayley's theorem said that every group is isomorphic to a group of permutation. So for given a group G, finite group G, I define SG. So this consists of set of all bijections between the set G to G. Now for each element G belongs to G, we define a function phi G that takes any element A belongs to G to AG. We are right multiplying by G. One can prove that this is a bijection. Therefore, this phi G is an element of SG. So we define a map psi from G to SG. Okay. So how G goes to phi G. Okay. So one can prove that this is a group homomorphism and it is a injective also. Okay. Therefore, so like you have a group and you have another group. If you have an injective homomorphism here, then if you look at the image here, image will be a subgroup of the codomain which is isomorphic to this group. Therefore, G is isomorphic to a subgroup of SG. Okay. Okay. Now so this prove that any group we don't need a finiteness here. Any group is isomorphic to a group of permutations. Now we proceed further. If order of G is n, then this SG, the set of all bijection between G to G, is isomorphic to permutations from 1 to n to 1 to n. This is straightforward to check. Now the symmetry group on n symbols is isomorphic to set of all permutation matrices n by n permutation matrices. Okay, and permutation. So now permutation matrices is a subgroup of GL and R. So in my video channel there is a video specially about permutation matrices. I will share the link in the description. Please check. Okay, so you start with the group G. This is isomorphic to a subgroup of SG. SG is isomorphic to Sn. Sn is isomorphic to permutation matrices. All the permutation matrices are invertible. Therefore, they are subgroup of GL and R. So we get G can be identified with a subgroup of GL and R. Okay, so therefore first option is true. Okay, so second option, you see, that is why I'm considering this as a separate problem. So this is alone very interesting. So let's see, there exists an infinite group such that every element other than the identity element has order 2. This many of you guys might already know. So you take an infinite set and consider a power set of S comma delta. So then this is a group in which every non-identity element has order 2 because A delta A will be empty set and empty set is the identity element here. Therefore, in this group, every element satisfies x square equal to identity. Okay, so this is an example. Next week, continue. The group GL2R contains a cyclic group of order 5. This is a very important problem in the many NBHM exam. They ask this question. So suppose A belongs to GL2 or has order 5. That means that if you so this is a group under multiplication. So if you multiply multiply A with itself 5 times, you will get identity element, right? So we need such a matrix. Basically, it means that if you have linear transformation, you compose it with itself for 5 times, or you keep applying it 5 times, you should get the identity element. Okay, we need such a linear transformation. So it is easy to construct. Using this approach, you can construct linear transformation satisfying a power n equal to I for any n. Okay, let's see how to proceed. So consider the linear transformation T from R2 to R2, which is rotation by 360 by 5. Okay, that is 70 degree. Okay, for example, you consider this matrix. So the corresponding matrix is given by cos 72 degree, sin 72 degree, minus sin 72 degree, cos 72 degree. Okay, then if you consider this matrix, this will satisfy the condition that a power 5 equal to identity. Okay, because like when you act suppose 1 comma 0 will first rotate to 72 degree, then some second time, third time, fourth time, fifth time it will come back to itself. Okay, so that is how it works. So and this particularly this matrix satisfies a power 5 equal to identity. You can play the game for any n. You just put the n here. Okay. Okay, so let's continue. So you can pause here and check how this linear transformation works. Okay. So let A be a Nbn matrix with real entries. Which of the following statements are true? So basically they are want to relate a rank of A transpose A and rank of A. Okay. Again, I put a description to a video where we proved that rank of A transpose equal to rank of A. In that video also I said this is a very important result. Now you are seeing it is asked in Nbhm. Okay. So I put the link in the description. Please check. Now, so I have proved rank of A transpose equal to A. Now, if you replace the role of A and A transpose, you get rank of A transpose A equal to rank of A transpose. So, rank of A transpose means this is, you can say this is dimension of column space of A transpose, but the dimension of column space of A transpose is equal to dimension of row space of A. Okay, but that is again another definition for rank. Rank of A equal to dimension of column space equal to dimension of row space. Okay, therefore we get rank of A transpose equal to rank of A because the column space of A transpose equal to row space of A. Okay, so we get this result. So the option B is true. Okay, let's see this problem one by one. Let x naught belongs to R cube be the column vector such that x naught transpose equal to 1 1 1. Let a v equal to set of all matrices vanishing at this point x naught. What is the dimension of v? Okay, so let's do this problem. So x naught equal to 1 1 1 column vectors. So you take this matrix A to be arbitrary 3 by 3 matrix. We want to understand when A x naught equal to 0. So suppose A x naught equal to 0, that means that if you act this matrix on this vector, you should get 0. This is x naught. So if you act this matrix on this vector, you get A plus B plus C equal to 0, D plus E plus F equal to 0. Maybe here you want to put the vectors 3. Okay, that is understood. So basically we get sum of the for some of the rows is sum of the entries in each row is 0. That is the condition we are getting. So from that we can, so if you equate this number to 0, this number to 0, this number to 0, then we can replace C by minus A minus B and the remaining entries also replaced suitably. So only these numbers are variables, independent variables. These are dependent variables. Therefore dimension V is 6. Okay. Okay. So let's do the next problem. Let A equal to this 2 by 2 matrix, then the options are A is diagonalizable. There exists a basis of R2 consist of eigenvectors which are orthogonal. W1 transpose W2 equal to 0 means that inner product W1 and W2 equal to 0. Then there exists a matrix B belongs to GL2R such that B cube equal to A. Okay, so this is a real symmetric matrix, therefore it is diagonalizable. If you calculate the eigenvectors of a real symmetric matrices, they always be like they are orthogonal, so that you can check. Therefore first two options are true. So let's move on to the third option. There exists a matrix B such that B cube equal to A. Now A is diagonalizable, therefore there exists an invertible matrix P such that PA P inverse equal to diagonal with the diagonal entries are eigenvalues. Okay. Now you consider this new diagonal matrix D where diagonal entries are lambda 1 power 1 by 3, third root of lambda 1, third root of lambda 2. Okay, so what are this number? So you consider this polynomial x cube minus lambda 1, x cube minus lambda 2. This is a polynomial of odd degree. Okay, so it will have a real root. So this is that real root. Okay. So okay, so now if you consider D equal to this diagonal matrix, then T cube will be lambda 1 lambda 2. So basically you have to take the cube third power of the diagonal entries, you get this matrix. Now B equal to, we take B to be P inverse dP and we claim that B cube equal to A. Okay, so now B cube equal to, if you take the three powers P cube, P inverse dP, P inverse dP, so these things are cancelled, so you get P inverse time D times P. Okay, so this D cube is this diagonal matrix lambda 1 comma lambda 2, P inverse diagonal lambda 1 lambda 2 P is precisely A. You can send this P, So this P will come here P inverse, this P inverse will come here P. So yeah, we get this matrix is equal to A. Therefore, there is a matrix P cube such that there is a matrix B such that B cube equal to A. Okay. Okay, so we have solved this problem. All the options are true. Let's move on to the next problem. So now if yeah, let's try to continue. Let f be a function that is known to be analytic in a neighborhood of origin in the complex plane. Furthermore, it is known that for n belongs to n, f and nth derivative evaluated 0 is this number. Find the radius of the largest circle centered at the origin inside which Taylor series of f defines an analytic function. Basically, they are asking for radius of convergence. Okay, this is the geometric description of radius of convergence. Okay. So now we know that the Taylor series expansion is around 0 is given like this. Fn of 0 by n factorial into z power n. Okay. So it is given that this coefficient is this number. So if you want, so we know how to calculate the radius of convergence of power series of the form summation a n z power n. So what is a n? A n is this term. This is f n of 0 by n factorial. Okay, so this term you have to divide by n factorial to get the coefficients a n. Now we know ratio test, root test to calculate the radius of convergence. We use that result. Okay, so if you simplify this expression, a n is n plus 1 by n whole power n square. So whenever n powers comes in the power, it's better to use the root test for the calculate the radius of convergence. So 1 by r equal to limit n tend to infinity mod a n whole power 1 by n. So this 1 by n and 1 n will cancel. So you get e. So r equal to 1 by e. Okay. So this problem can be done easily. So next we move on. Which of the following statements are true? F of x equal to sine square x is uniformly continuous. So that is true because if you look at the derivative, it is 2 sine x cos x, and mod sine x is less than or equal to 1, mod cos x is less than or equal to 1, therefore mod f prime of x less than or equal to 2. So if a function has bounded derivative, then it is a Lipschitz function. So again, Lipschitz function is a very important concept. So I have made 2 videos on Lipschitz function. I have given the link in the description, so please check this video before the exam. Okay, so let's continue. So therefore Lipschitz functions are uniformly continuous. Okay, therefore the first option is true. So the second option is true, third option is false. Let's see why. Second option is f from open 0 comma infinity to r is uniformly continuous, then limit x tends to 0 f of x exists. So let's see why it is true. So we have a very nice result, very important result. Let x comma dx, y comma dy be metric spaces, and y is complete. That is very important. This codomain should be complete, and let a subset of x. If f from a to y is uniformly continuous, then f can be uniquely extended to a continuous function g from a bar to y. Okay, and g is a uniformly continuous function. So if uniformly continuous on a, then you can extend it to a bar. That is the main thing. So the closure of open 0 comma infinity is close 0 comma infinity. Therefore limit x tends to 0 f of x exists. Okay, so you can extend it to 0 means that limit extend to 0 f of x exists. Next, if f from open 0 comma infinity to r is uniformly continuous, then limit extends to infinity f of x exists. That is not true. You can take the identity function, limit extends to infinity, x is infinity. Exists means it should exist and finite. Okay, so that option is false. So let's move on. Yeah. Okay. So which of the following statements are true? Log x less than or equal to x by e, log x greater than or equal to x by e, then e power pi greater than or equal to pi e. Let's do e power pi. So these two are completely independent problems. Okay, so that is why I have given different numbers. So let's see first this problem, e power pi greater than pi power e. Note that e power x greater than 1 plus x for x not equal to 0. When x equal to 0, they are equal. Okay. So how to prove that? We use the derivative technique. So you take f of x to be e power x minus 1 minus x. Okay, we claim that this function is greater than or equal to 0, strictly greater than 0 for x not equal to 0. Okay, so you calculate the derivative, it is e power x minus 1, and derivative 0 only if x equal to 0. Okay, so at the point 0, we get f of 0 is 0. Okay, that is one observation. So now let's see. So if you look at the graph of e power x, so it will be like this. So this is 1. In minus infinity to infinity, it is increases to 1. After from minus infinity to 0, it is increases to 1. After minus infinity to 0, in 0 to infinity, it is increases to 1. In other words, in open 0 comma infinity, e power x value is strictly greater than 1. In minus infinity comma 0, the e power x value is strictly less than 1. Okay. So e power x strictly less than 1 on minus infinity comma 0. Therefore, in this interval, derivative is less than 0. Therefore, function is decreasing. This function is decreasing in this interval, and e power x is strictly greater than 1 open 0 comma infinity. Therefore, derivative is positive. That means that function is increasing. Increasing here, decreasing here, and at 0 it is 0. So it is decreasing, and it is 0 here means it is positive. So from positive only something can decreases to 0. Once it is 0, it is start to increasing on open 0 comma infinity. Basically that means that this function is a non-negative function. Therefore this inequality holds true whenever x not equal to 0. Note that this is open interval, so at 0 we get the derivative 0. Okay, so now this inequality is proved for x not equal to 0. Now you put x equal to pi by e minus 1. Note that this is not equal to 0, so you can substitute the value in this interval, in this inequality. So you, if you simplify, you get e power pi greater than pi power e. Okay, yeah, so this result is true. Now let's see why first two options are true. So now again, so this is a function, this is a function, you want to see which function is greater than what function. So use the same derivative technique. So you can see that you can, I mean, use like now we did this problem in using this idea, you use the same idea. Okay, so consider the difference of these two functions, f of x equal to x by e minus log x. Then you can see that at derivative at x equal to e, the function derivative is vanishes. Again, like by splitting the intervals like this, you can conclude that option 1 is true, second is false, and we proved that C is true. Okay, same idea. So whenever they are telling us to giving this kind of inequality, you have to compare, you have to look at the difference of that function and look at the derivative and equate it to 0 and see wherever they are increasing and decreasing. You can argue like that. So let's continue. Yeah, this is a nice problem. Let R1, R2, etc. R and B an enumeration of rationals in the interval close 0, 1. For n belongs to n and for each x belongs to close 0, 1, we define a sequence of function fn of x equal to 1 if x equal to R1, R2, etc. Rn and 0 otherwise. Note that as n tend to infinity, this x the places at which the function takes 1 is increases to rational numbers. Therefore, the limit function of this sequence of function will be Dirichlet function. Okay, so what is a Dirichlet function? That is 1 in rationals and 0 in irrationals. Okay, so that is our first observation. This sequence of function converges to Dirichlet function. Okay, so the question is about Riemann integrability of Fn. The function Fn is Riemann integrable over the interval close 0, 1. Okay, so let's see why it is so. So the sequence of functions, each fn is discontinuous only at this n points. Otherwise, it is constant function 0. Okay, therefore, at finitely many places, the sequence of function vanishes. I mean, discontinuous. So now we have this nice result. F is Riemann integrable if and only if f is continuous almost everywhere. So almost everywhere means it is continuous outside a set of measure 0. If you don't know what is measure 0, finite sets are measure 0, countably infinite sets are measure 0. So this is a finite set. Okay, so this function discontinuous only on a finite set. So discontinuous only on a set of measure 0. Therefore, it is continuous almost everywhere. Okay, therefore, first option is true. Each fn is Riemann integrable because it is continuous almost everywhere. And the second option is the sequence fn pointwise convergent and the limit function is Riemann integrable. This is false because limit function is Dirichlet function. Dirichlet function is nowhere continuous. Okay, so this you can prove by using you take a rational number and you take a sequence sequence. We prove it in the some other problem in the future. Anyway, so this function is nowhere continuous. Okay, nowhere continuous means its set of discontinuous closed 0 comma 1 which has positive measure. Therefore Dirichlet function is not Riemann integrable. Therefore this function, the limit of this function is not Riemann integrable. So option C is true. The sequence of function fn is pointwise convergent but the limit function is not Riemann integrable. Okay. Okay, so let's continue. Move on to the 19th problem. Let x be a set and V be the vector space of real valued functions defined on Ex with the pointwise addition and scalar multiplication. So assume that if f belongs to V, then f square belongs to V and mod f also belongs to V. Which of the following statements are true? If fg are in V, then fg belongs to V. If f and g are in V, then maximum of f comma g belongs to V. If f belongs to V, then fq belongs to V. So let's see how to proceed. So if f and g are there, since it is a vector space, f plus g will be there. So if f plus g is there, by this property, its square will be there. Okay, so we got f square plus g f square plus g square plus 2fg belongs to V. Now f belongs to V and g belongs to V, therefore f square belongs to V, g square belongs to V, V is a vector space, therefore their sum is in the V and their difference like their negative also in V. So minus of f square plus g square is an element of V. So if you subtract minus of f square plus g square from this element, you get 2fg belongs to V. It is a vector space, you can scale it, you can multiply by 1 by 2, you get fg belongs to V. Okay. Okay, so now we can immediately argue part C. If f belongs to V, then f square belongs to V, then f into f square, you get f cube also belongs to V. Okay, so first and third are true. Let's look at option B, maximum. Note that maximum has this nice representation. Okay, similarly you can write represent for minimum also. So this involve only f of x, g of x and modulus and differences. So it is some scalar. So since V is a vector space and modulus is belongs to V, whenever f belongs to V, we conclude that maximum is also belongs to V. Okay. So given constraints are enough to given hypothesis is enough to conclude that maximum is also element. Okay, so I will stop with the 20 problem, then we in the next video we will see the next 20 problem. Right, find the number of elements conjugate to this particular permutation. So we have nice result in, so two permutations are conjugate if and only if they have the same cycle decomposition. Okay, so if a permutation conjugate to this permutation, that also should be of 7 cycle. Okay, so let's count how many cycles, 7 cycles are there in Sn. Number of R cycle in Sn, there is a nice formula, that is 1 by R times n factorial by n minus R factorial. If you substitute the value here, number of 7 cycles in S7 is 6 factorial. In general, number of n cycle in Sn is n minus 1 factorial. Okay, so we'll continue the next problem in the next video. If you learned something new in this video, please click the like button and share with your friends and subscribe to my channel. Thank you.